Hi, this video describes the set abstract data type. Set is a different abstract data type than the ones we've covered, but it's pretty similar to a map, as you'll see. The idea of the set ADT is to represent the concept of a mathematical set. You know, in mathematics, we have sets, we have curly braces to say the elements of a set. A set contains elements, so the data objects that are inside a set are called elements. And a math set cannot have duplicates. So every element is either in the set or not in the set. Namely, that element is in there just once. There's no such thing as duplicated values in a set. This is similar to a map. In a map, every key is unique. Remember that in the map, you can't have duplicate keys. Every key is either in there or not in there. And that's just the same as every element is either in a set or not in a set. So we could say that a set is a lot like a map that only has keys and does not have values. If we take the map idea and just ignore the value part entirely and only focus on the keys, that's almost a set. Here are the operations that we'll define for the set abstract data type. As usual, you can create an empty set. That would be the constructor. We have a size operation to return the number of elements in the set. There's a contains operation, so given x, return true if x is an element inside the set and false if x is not in the set. We have an add operation, add x, adds x to the set if it's not already present, and returns true if x actually got added and false if x was already there and we didn't change anything. Finally, remove x, removes x from the set if it was ever present, and we return true if x actually got removed, and false if we didn't do anything because x wasn't there to begin with. We can implement this set ADT as an adapter of a map. Remember that an adapter is a container that uses some other pre-existing container to implement a new and different interface. We can use that idea here. We can use a map, which could either be a binary search tree map or a hash table based map. We're going to use that map to implement the set operations. As usual with these adapters, we have to define the correspondence between the concepts in the two data types that we're working with. The correspondence is that an element x is in the set corresponds to the concept that a key x is in the map. So basically the elements of the set that we're implementing correspond to the keys in the map that we're using, and we're going to ignore the values entirely. We'll just put some kind of dummy holder value in there and not ever use it. In particular, I'll use Boolean false. That Boolean false is just the simplest value I can stick in a value field. So now let's go through how these operations would work. Again, we're implementing the set data type. T is the data type of an element of the set. So there's one private data member. It's a map, and the key type is T. So the data type of one element of the set is the data type of one key in the map. And then I just have this throwaway bool that's basically ignored for the values. So the set constructor just calls the map constructor. It initializes a new empty map. The size operation for the set just returns the map size. So if we use a binary search tree for the map, then that takes constant time. Same thing for the hash table. Those two operations are constant worst case time for the hash table as well. The contains operation, given x, decide if x is in the set. We just use the map contains operation. It's one line. And with a binary search tree based map, that's logarithmic time. And with a hash table based map, that's constant expected time. To add an element to the set, we just call the map insert operation. We insert key x and then false. This is this kind of throwaway placeholder value. So we just call map insert, and that's logarithmic time with a binary search tree and constant expected time with a hash table. Finally, remove is the same idea. In order to remove from the set, we just remove from the map object that we have. And again, with a binary search tree, that's logarithmic time, and with a hash table, that's constant expected time. So here's how these compare. It's efficient no matter how you cut it, but we get the same trade-off we had with maps because we're basically just calling a map operation for each one of these set operations. So whether you use a binary search tree or a hash table, you can construct a set in constant time. You can get the size of the set in constant time. And then with the binary search tree, search, add, and remove are logarithmic worst case time each. And with the hash table, those are constant expected time.